So this is the second part of a podcast on assessing model risk on dependence in high dimension. In this part 2 of the podcast, I will focus on value at risk. The setting is very similar, but I will repeat some notations so that they can be more or less self-contained, but the method and the rearrangement algorithm that we will need to solve the value at risk case have been explained in the part 1. So let's repeat the objective. Our objective is to model uncertainty now on the value at risk of an aggregate portfolio. Aggregate portfolio, the sum of the individual dependent risks. What I want to do is to estimate the value at risk at some level, so a quantile at some level of the sum, x1 plus x2 plus xd. One possibility, you fit your multivariate distribution, you compute the quantile within this multivariate distribution that you fitted, and then you calculate it. But how about model risk? How wrong can we be? And what we did is we focused on assessing model risk on dependence. So what if you have uncertainty on dependence and you want to know what is the maximum value at risk and what is the minimum value at risk for the sum if I don't know perfectly the dependence? And we're going to take these bounds over all random vectors that agree with the available information. We have two main findings and important findings. Current value at risk regulation, if you think about Basel II, Solvency II, they want a 99.5% confidence level. It's a very high confidence level. And what we find is when you go as far in the tail with a 99.5% quantile on the sum of your risks, it's subject to very high model risk. So, and even more surprising, what we find is that even if you fit a model, even if you have a lot of data, you still have some areas where you won't have data. If these areas are in the tail, you will have a very high model risk on the estimate of your value at risk. And the second part, the second finding that we find is that fitting a multivariate distribution is actually useful, can be useful for value at risk, but not for value at risk at 99.5%. You can do that for a value at risk at a lower confidence level. Even 95%, we will illustrate in the example, already the model risk estimating a 95% value at risk is reduced a lot. Some definition that we will need, value at risk is a quantile at some level Q belonging to 0, 1. The value at risk is a quantile of the distribution of X. The tail value at risk or expected shortfall is going to be the average of the value at risk beyond some level Q. And I'm going to use at some point the left tail value at risk, which is the average of the quantiles below some level. But the ones that are used for capital requirements are essentially the value at risk and the tail value at risk, and the also called expected shortfall. In part 1, we focused on risk measures that satisfy convex order. But in fact, value at risk does not satisfy convex order. And one of the consequences is that the maximum value at risk, so the risk is maximized not in the comonotonic scenario. I'm going to write SC to refer to the comonotonic sum where x1, x2, xd, my d-dependent risks, are moving together. The maximum correlation case. And if you think about the metrics that we've introduced in part 1, it means that all x1, x2, xd are ordered in the same way. And we compute the sum for this comonotonic scenario, and that's what we call SC. In fact, to maximize value at risk, what we will find is that we can start from this comonotonic scenario, but then we can make it even more risky. And the way to increase the risk is to look at the tail beyond the level Q that we are interested in, and we're going to change this comonotonic structure to make it flat. And I'll explain more what we mean here in the examples. Already, we can illustrate it with two risks. Two risks that are uniform 0, 1. So these are just x1 and x2, two random variables, and we assume they are comonotonic, so perfect correlation. And when we look at the value at risk of the sum in the comonotonic case, it's easy to verify that at the level Q is just 2 times Q. Now, this is not the riskiest situation because I said value at risk is not maximized for the comonotonic scenario. So there exists another scenario that's going to make it even bigger. And this is the scenario represented here. So what does it mean? This is x1, this is x2, and they are comonotonic below the level Q. But what happens above the level Q? They are moving in opposite order. The two tails, instead of being comonotonic, they are antimonotonic. They are in reverse order in the tail. And this is the surprising feature. To maximize value at risk, because this is the riskiest dependence, so this is where we maximize value at risk. To maximize value at risk, we're actually going to make the negative correlation in the tail. Remember, negative correlation when we were looking at the variance minimizes the risk because it minimizes the variance. Here, to maximize value at risk, we have this negative correlation. And when we compute the value at risk, we find that it's 1 plus Q in this situation, which is strictly bigger than the comonotonic scenario. Now, how about in higher dimension? How are we going to do? The idea is very similar. We look at the value at risk of the comonotonic sum. Now we may have D risks, where D is bigger than 3, and we represent this quantile function for the value at risk at level Q of the comonotonic sum. And we know, at least on the uniform, we've already seen it, that the value at risk is not maximized by comonotonic scenario. So we know that the quantile that we obtain here, which is the quantile for the comonotonic scenario, is not maximum. So there's another way, another dependent structure that can make this quantile bigger. And what do we know about the quantiles above this level? We know that the average is actually equal to the tail value at risk. Tail value at risk is the average of the quantile below some level. So the average of all these values in the gray area is exactly the tail value at risk. Now, value at risk is always smaller than tail value at risk because tail value at risk is the average of the value at risk that are bigger than this one. So we know for sure that the value at risk will always be smaller than the tail value at risk. Now, what we can find is there exists, at least we're going to try to look for a dependent structure such that the quantile, the value at risk of the sum, is not anymore equal to the value at risk of the comonotonic scenario, but goes up to the tail value at risk of this comonotonic scenario, which is the maximum tail value at risk. And here it is. Can we find a dependent structure that now I'm going to call S star, such that the value at risk for this dependent structure, and this is going to be the riskiest dependent structure, is exactly equal to the tail value at risk. And theoretically, we're able to do, so not only this one, if it exists, we know if it exists, it's the maximum value at risk. And the same thing in the lower part, if you want to make the minimum value at risk, you're going to take this level and make it as flat as possible. And it's possible to show that if you average them, this is the lowest possible value for your value at risk. And that's why we get this theoretical result that gives us bounds, analytical bounds on the value at risk at any level Q. What is the constraint? We assume that all the risks have fixed marginal distribution, and we're optimizing over all possible value at risk, fixing the marginal distribution, and allowing for any dependent structure. When we look for the maximum, we find that the maximum is the average of the gray area, the gray line here, which are the value at risk above the level Q, B, which is the upper bound, and A is the lower bound, which is the left tail value at risk average of the quantile below the level Q. Now, these bounds are theoretical, and they will be sharp if you can find a dependent structure such that they are exactly attained. In some cases, we can show they are attained, and in some cases, it's still an open problem to know whether they are sharp or not. But what we can do is apply the rearrangement algorithm developed in the previous part, in part 1, to the tail. So we're going to apply the rearrangement algorithm in the tail above Q and below Q and make it as flat as possible, which means applying the rearrangement algorithm to minimize the variance in the tail and to minimize the variance in the left tail. What do we obtain? So I have an example. I'm not repeating this rearrangement algorithm, but what we did is we consider the same example as before. We take 20 normally distributed risks, N0, 1. We assume the marginal distribution are given. So N0, 1 for the first X1, X2, XD, they all have a fixed marginal distribution. And we are asking ourselves, what is the maximum value at risk, what is the minimum value at risk? What we did, we took a simulation technique where we simulate 3 million of X1, 3 million of X2, 3 million of XD, and we put them in a matrix. X1 being the first column, X2 being the second column, and you have 20 columns and 3 millions of rows. Then you organize the data so that it's comonotonic. So you start from the comonotonic scenario. You cut the matrix so that below the level Q, you're going to apply the RA in this zone, and above the level Q, you apply the RA, the rearrangement algorithm, you apply it in the upper zone to make it as flat as possible. So it's really based on this idea where you cut at the level Q and you apply the rearrangement algorithm anytime you are above this level Q and anytime you are below this level Q. So you have your matrix and you apply it in the two zones separately. And then what do you find? Depending on the level where you cut, you will get different bounds. So if you cut at 95%, we find that the lower bound, there exists a dependent structure among your data set that gives you a value at risk of minus 2.17, a negative value. If there exists also a dependent structure that will be able to achieve a value at risk of 41.3. And it turns out that these two values are actually exactly equal to A and B. So for the normal distribution, at a very, very high level of accuracy, we're able to show that the rearrangement algorithm is able to get exactly the analytical bounds. So they are good proxy, at least for some type of distribution, and we discussed this more into a research paper. So this is what happens with 95%. Now, what happens with 99.95%? We find that the upper bound, the maximum value at risk, is increased a lot. So now, your capital requirement, if they are based on value at risk, are not anymore capped at 41, they are equal to 71.1. You can find more examples of this in the paper of Embrechts, Puccetti, and Rüschendorf, as they are the one who actually developed this idea of finding the maximum value at risk and minimum value at risk for when only marginal distributions are known. Now, what do we observe from these numbers? These numbers clearly shows that they are really wide. And they are actually too wide to be really useful in practice. And one of the arguments we could have, we can say, this is because we ignore all the information on dependence. The only thing I did here is assuming I have normally distributed risks. But I haven't assumed any structure among the risks. So similarly as before, we want to add information from a fitted model. And we did that for the normal distribution. So for instance, with two normal distributions, the same thing as before, we have our data set and we have an independent structure, but we trust the independence, the dependence, which is independence here, in this area only. So we have our trusted area with independence copula, and we trust our dependence only there. And now within these constraints, and this constraint can be small if the beta, which is the quantile level, which will give you the size of this box, the size of the fixed area, the trusted area where you trust the dependence. So if this trusted area is very small, that means you don't trust anything and you have no information on the dependence. So you're back to the previous case where you only trust the marginals that are normally distributed. And if you make this red box very big, that means you trust the independence assumption everywhere. And so we've developed an algorithm to solve this problem, where we assume marginal distribution are known. Joint distribution is known only in this area F, and we know the probability to be in F. We want to find the maximum value at risk, the minimum value at risk, consistent with these three points. And that's what the purpose of this paper that we developed with Steven Vanderfel. We adapted the rearrangement algorithm that was developed in the case for the variance bounds with dependence constraint to get bounds on value at risk in this particular case where we have additional assumption on dependence. Dependence is trusted in this area. And we also in the paper, and I'm not going to present them because they are slightly complicated, but very practical in the sense that very easy to implement, we provide theoretical expressions as the value at risk of a mixture for the lower and the upper bounds. How about numerical results? So we take away 20 independent normal 0, 1, and I'm going to assume that they are independent only on the area F. At least that's where I trust the independence. Anywhere else, I don't trust it. If this area F is full space, because U is the complementary, is the uncertain area, untrusted area, so here you have full trust on your model, the untrusted area is empty, the trusted area is the full space, beta is equal to 0, which means you take the quantile at 0 and the quantile at 1, so your red box covers the full space. In this case, this is the value at risk of the sum of 20 independent normal 0, 1. At 95%, at 99.95%. How about if now you don't trust anything, you trust only the marginals? You will find back in this last column, you will find back the bounds that we found in the case where you only trust the marginals and you have no trust at all on the dependence structure. There's a huge gap in between. You can see that the person who's just going to fit the model and get 12.5 is going to be very far from the maximum risk that is possible if you feel that dependence information cannot be trusted at all. And so these are the 12.5 and 25.1 that we find here. Now, how about if we add information, and this is where it becomes really interesting and quite surprising at first, and then when you think about it, it starts to be, at least you can find explanation for that. If I define my trusted area such that the probability to be in the trusted area is 98%, which means I trust the independence assumption in 98% of the space. I compute bounds for the value at risk at 95% and the bounds on the value at risk at 99.95%. What do I find? I find that at 95%, the bounds are actually really close to the assumption that I have 20 independent normal distribution. So here, for instance, it actually shows that the information that you add on this is the independence assumption among my 20 risks, even if it covers only 98% of the space, because you don't have data everywhere, you just have data that covers 98% of the space, you still have very small bounds, which means this is an accurate estimate. Now, how about you want quantile deep in the tail, which is closer to what the regulators want? They want these extreme quantiles with very high confidence level at 99.5% or higher. What do we find? We find that the bounds are between 24.2 and 71.1. This 71.1 is exactly the same as the 71.1 here, and the same as here. So what do we find here is that the maximum value at risk, which is the maximum risk, and the maximum capital requirement that you may want if you don't trust dependence at all, which is the last case, and we say, okay, it's not good because you don't trust dependence at all, but now I'm saying, yes, I trust dependence, I have a lot of data, I fix the independence copula everywhere, so I know my copulas are independent. in 98% of the space, but still the maximum value at risk is 71.1, which means we have absolutely no improvement on the maximum value at risk possible, and that means that the risk at very high probability level for the value at risk, despite all the information that you add, the bounds are still very wide. So the bounds that you obtain with the method of Embrecht, Puccetti, and Rischendorf that ignore all information on dependence are actually the best you can do if you're looking at a value at risk at a very high level. If you look at a value at risk at a lower level, then it would make sense to develop a model and to incorporate information on the dependence. Even if your model, you trust it only in 80% of the space, you would still have more reasonable bounds. So to conclude and to remember from this part 2, I would say maximum value at risk is not caused by the comonotonic scenario. There are riskier situations, and these riskier situations are obtained when the correlation in the tail is actually negative among the risk. Precisely, it's obtained when the variance is minimum in the tail. And so we use the rearrangement algorithm techniques, but only in the tail of the distributions. Bounds on value at risk stay very high. They stay very wide even when you know the dependence structure almost everywhere. So if you're really only interested in value at risk at 99.95%, there's no point to spend a lot of time fitting a multivariate distribution and developing a very fancy multivariate distribution if it covers, if you are able to trust it only 98% of the space. So these are general conclusions that can be applied to both part 1 and part 2. What we did, the general idea is to assess model risk with partial information on dependence and given marginals. We developed definitely 2 methods. One is purely non-parametric using the RA only, and one that is based on closed form expression or expectation that can be evaluated from Monte Carlo. We have designed an algorithm that works for variance, tail value at risk, and you can extend it easily for more risk measures. Many challenges are left. In fact, choosing the area F is a really difficult problem to solve. We found also that sometimes you don't have enough data when you observe, especially when you look in the tail, so you may not trust your marginal even there. So you might either rediscretize from the marginals to increase the number of observations, or you may amplify the tail by using some distortion measure or extreme value theory. Finally, the way we incorporate dependence is actually very particular. We incorporate dependence only on this trusted area where we fit the model and we say we trust our fit in this area F. There are other types of dependence and information that can be incorporated. And one of them that is very promising is to incorporate experts' opinion. Because what is in the tail may not come, what can happen in the tail may not come from observed data and may not come from a fitted model, but it may come from other events that you may be able to predict, or at least to have some idea what happens if the S&P 500 goes by, increases by 100% or decreases by 50%. So there are some extreme scenarios that we may know even though we have never observed, and you can incorporate, if you know what's going to happen in these scenarios, you may know the dependence between the risk under these scenarios, and so you might incorporate them as your trusted area. Now, the dependence that you fix in the trusted area may come from experts' opinion instead of coming from a fitted model. Another thing, if you're interested in bounds on value at risk, it turns out that to decrease the uncertainty on your value at risk bounds, you need to incorporate information from the tail, so using, for instance, experts' opinion, or you may want to use a global measure. So, for instance, you may say that I know the variance of the sum, I have some idea of how it has been estimated in the past, or I know the correlation metrics, what is going to be the maximum value at risk and the minimum value at risk that are consistent with this information. And we have developed some recent work with Ludger Rüschendorf and Steven van der Velde. And we are also thinking about adding additional information on higher moments with de Nuit and van der Velde again. Finally, I would acknowledge the different agencies that have supported this research: Society of Actuaries, the Canadian Institute of Actuaries, the Global Risk Institute for a project on systemic risk, and NSERC that is funding my research. More information you can find on many references that are joint project with Steven van der Velde, who has been my main collaborator on this topic, and other collaborators that have been cited in the presentations. Thank you very much.